This is a formal example that says, what is the root mean squared speed of a molecule in a sample of pure gas as a function of temperature? And I said in the last example, well, that there are these four expressions that are all related to each other. This one was the average kinetic energy in a molecule. This was the amount of kinetic energy in n molecules, which maybe would be average if n is small, but if n is a large number, you don't have to say average. This expression is that same thing, but expressed in terms of moles, which lended itself to this expression here for the amount of kinetic energy per mole. And so now I could state, well, for this formal example, let's guess which one of these four am I going to start with in the slide based on the language that is there. Well, I think the clue to the answer for that is that we're talking about a molecule, a single molecule. So that's like capital N is equal to 1, which is really like this original expression here, and which means we're going to be talking about averages. And that might make sense because we're looking at getting towards an expression for the root mean squared. Mean might sound really mean, but it actually means average, right? So we're really talking about the square root of the average of the square of speed there. And that's something we've kind of mentioned earlier. So how did I start this out here? Well, here's the 3/2 kT. Maybe not exactly right at the beginning there, but of these four that's up there, that's the one that's in here. And then setting that equal to the average kinetic energy, thinking about that in terms of the average of the velocity squared, which is actually basically the square of the root mean squared. But that times 1/2 an m gives you that kinetic energy. And so then you can do some algebraic manipulations there. Oh, actually, I think there's a mistake in this slide that maybe you want to don't copy this one into your notes, because there should be a square root actually here on this one, because I square rooted both sides and somehow forgot to square root that side, because that then implies that VRMS is in fact equal to the square root of 3 kT over m. So this is one of the formulas that we had on the key concepts slide, which is useful to us because we can now plug numbers into that to answer the question of what the RMS speed of a molecule in a gas is going to be. And I'm presenting that here because those are the kinds of questions we do see in this class and are going to see in some examples.